today. I've posted a problem up here. I will tell you most of it if you haven't read it yet. There's an island with 1,000 people. Their religion forbids them to know their own eye color or discuss the topic. Everyone can and does see the eye colors of all the other residents, but doesn't have any way of discovering their own eye color. There's no reflective surfaces. If they do discover their own eye color, then their religion compels them to commit ritual suicide at noon the following day in the village square for all to witness. All the tribespeople are highly logical and devout, so if they figure out what their eye color is, they will follow the procedure. So on this particular island, there's 100 of them with blue eyes and 900 with brown eyes, although they don't know those statistics. One day, a blue-eyed foreigner visits the island and wins the complete trust of the tribe. One evening, he addresses the entire tribe to thank them for their hospitality. However, not knowing the customs, the foreigner makes the mistake of mentioning eye color in his address, remarking how unusual it is to see another blue-eyed person like myself in this region of the world. What effect, if anything, does this faux pas have on the tribe? I don't want to talk about it yet. I want everybody to think about it. And you can talk with your neighbor, and then we will discuss as a class. Okay, let's collect some possible effects. So what are some possible effects? Who wants to suggest one? Okay, so we have one possibility that 100 days after the address, all the blue-eyed people commit suicide. Any other possibilities? There's no effect because no new information is introduced because everyone already knows that there's a blue-eyed person. Okay, any other possibilities? Yes. Everyone expects him to commit suicide. Okay, what else? Any other possibilities? Everyone commits suicide. Okay, here are the possibilities we have. Did anybody see The Croods? The movie The Croods? Did anybody see The Croods? Raise your hand if you saw The Croods. No one in here has a child. Okay. All the stories that the Nick Cage character tells end in everyone dying. It's pretty funny. Okay, so I would like you to vote. Which one do you think is true? Number one. Okay, looks like we have at least 2/3 of the class voting for that. Okay, number two. 100 days after. Okay. And number three. Everyone dies. Okay, so we had a really small minority voting for number two. So number one seems to be plausible, right? Because everybody knew there was a blue-eyed person. Can the people who voted for number two, can someone prove it? Or make an argument? You want to make an argument? Yeah. Right. Yeah, so exactly. So here's an inductive proof. So we suppose that the tribe has n blue-eyed people for some positive integer n. Then n days after the traveler's address, all n blue-eyed people commit suicide. So when n equals 1, the single blue-eyed person realizes that he must have blue eyes, so on the first day he commits suicide. If n equals 2, the second, each person knows that there's already a blue-eyed person, and then they realize that if no one commits suicide on day 1, that they must actually also have blue eyes, so they both commit suicide on day 2, and so on. So whatever number there is, they will realize on the n-minus first day, if no one commits suicide, that there must be n of them, and they'll commit suicide on the next day. So they'll all figure it out, and then they'll commit suicide. So this actually could also imply that, what, all the rest of the people would realize that they are brown-eyed, right? If there were only two eye colors. So the very next day after that, all the rest of the people would die. So, in fact, all three of them are reasonable arguments. Yes? That's a good question, but we'll just simplify the world and say there are only two eye colors, and then we don't have to argue about the puzzle. Yes? Very good point. So a brown-eyed person could come to the same conclusion, right? Yes?
The brown-eyed people always see one more blue-eyed person than the blue-eyed people see, so they have different information to start with.
Okay, so brown-eyed people have different information because they actually see one more blue-eyed person than the other ones. So let's see. Let's just assume go back to the case of one blue-eyed person and I'll say 3 brown-eyed people. Okay? And on day 1, that blue-eyed person would commit suicide because they don't see any other blue-eyed people and they know there's at least one. And all the other people see him commit suicide. So if there was more than one, they would know that he wouldn't have committed suicide because he would have known that there was another blue-eyed person, so he wouldn't have done it on day 1. So possibly that would extend inductively. But what does this argument actually do? So how does it work? Are we actually like doing induction? Like are people going from 1 to 100 people? It's a generalization. So we're making an argument based on the size of a group. And we're saying we can solve a small problem for n equals 1. We know what's going to happen because we can figure it out. For a next size group, we can use the previous size group to figure out what would happen. Right? So this is what induction is. So induction figures out a base case that you know how to do and then advances to the next case. By the way, I'm not going to tell you which of these answers is correct. I'm going to point you to a web page that has a discussion about it, and you can go see what the solution to this puzzle is. So I just wanted to intrigue you with a couple of examples of induction. Let me give you another one. So you guys voted for no effect, that it doesn't affect anybody. Mostly, that's a common sense argument because, you know, if you're not a super highly logical person, which most people are not, you're not even going to think about how many days it's been since the address and count anything. So there's plenty of interesting discussions around this puzzle. And it's related to a puzzle that Google asks people at their interview, which is in a village there's a bunch of couples, and all the wives know if any other man is cheating in the village. They don't know if their own husband is. And then one day a stranger comes to the village and tells them that at least one person is cheating. And then what effect does that have? It's a very similar puzzle. So anyway, so here's another proof. Can you prove that all natural numbers are interesting? Give it a try. I'd like to see what you try. So try to prove that all natural numbers are interesting. Just try. Don't ask me any questions. Make up your own definitions. Okay, let's hear some of your proofs. Who has one? Nobody could prove it? Yes. Okay, so we have sort of an arithmetic proof that all numbers except for primes are evenly divisible by other numbers. And the primes themselves are interesting because they can't be divided by other numbers. And then the other numbers are interesting because of like figuring out which primes they're divisible by. Okay?
So if you assume there is a first uninteresting number, then you say that's interesting. So it's not the first uninteresting number, and you just keep moving up.
Right, so that's a sort of a proof by contradiction, right? So figure out the smallest uninteresting number, right? And that's an interesting number because it's the smallest uninteresting number, and therefore it's a contradiction. So that's a fun little proof. Here's another one, which is very similar. Clearly 0 is interesting. Suppose that m is interesting for all 0 up to n. If n plus 1 was not interesting, then it would be the smallest number that wasn't interesting, and that's interesting. And that's a contradiction. This is a fun one, right? Okay, so but this works the same way as our proof by contradiction in logic, right? It works the same way in that we were actually trying to find two things that are opposites. This uses the strong induction hypothesis. So the last induction we saw actually starts with n equals 1 and grew to n equals 2, grew to n equals 3, went up by 1 every time, and only made an assumption about the group of the size right before it. In this proof, we're actually assuming that everything up to n, so 0 up to n, is interesting, and then we're doing something for n plus 1. So that's a stronger version of induction. It just means you have to assume more stuff before you can start doing it. So both of these are valid methods of induction. You can assume something's true for n and prove it true for n plus 1, or you can assume something for all the numbers up to n and then prove for n plus 1. So that's just two different methods of doing induction. Okay, here's another one. So we fix a positive integer n, show that it's possible to tile any 2n by 2n grid with exactly one square removed. So what we're talking about is here's a small example, right? So this is n equals 1, and this is a 2 by 2 grid. And if we take one of the squares off, it looks like that. So, but that's also the L-shaped piece we're talking about, right? That's an L-shaped piece made out of 3 squares. So already our first case that we look at is the case of an L-shaped piece, right? So we can cover it with an L-shaped piece because it is an L-shaped piece. Okay? See if you can figure out how to do it for 4 by 4. So that's for n equals 2. We have a 4 by 4 grid. Solve whichever one you feel like. See if you can prove it. Okay, so we have a solution. What's your name?
Robert.
By Robert. Last name?
Benson.
Benson. Robert Benson's going to show us his solution.
Okay. Basically, I proved that I saw that if you take this.
Hold on.
Sorry? Oh, okay. Then, basically, if you black out any square in this grid. So basically, if you were to black out any square in this grid, the square that you black out will be contained within one of the 4 bigger corners of the grid, which is a 2 by 2. So now what you have left is this big L shape, which I figured out you can make out of L shapes by doing this. Yeah, so now you have like new blacked out square and new L shape in the next size. So you can do that for the next size. You can just use this again. I think.
Yes. Yours different? Let's see yours. Here you go. Say your name.
Jack. Wingo. Alright, I'm Jack Wingo. And, alright. Thanks. Alright, so I just put mine in the top right corner, like that, and then I just like based on the original like square deal. I just kind of like I guess like tesslated them in this direction, and I just saw that the sides fit like that. And then if you just kind of like add it onto the sides for any shape, you can like replace it with more like L shapes. Well, not the same way, but yeah, that could be or yeah. It worked in, I don't know. Yeah, 4, but never mind. Yeah, 4x4.
Okay, good. So whenever we're faced with a new problem, we always want to try to do some examples until we understand what we're doing, and then we can try to generalize to some bigger problems. So a couple of you said you had general solutions. Are they different than Robert's? Okay, they're basically the same. So let me restate Robert's. This is basically what we do for induction problems. So this is a basic computer science principle. When we're going to solve a big problem, let's figure out first how to solve it for a small version. And then we try to figure out how to map the large problem into the small one. It's because small problems are usually easy to do, right? We can mess around with them until we figure out a solution, which is what we could do with the 4x4 grid. We can just, pretend to have L-shaped pieces and draw them and do it until we figure it out. And then if you figure out a bigger strategy that you can do for an 8x8 and then also for a 10x10, then you actually have something that might actually be able to do for any size. So what you need to do when you're doing this is actually do it for consecutively larger problems until you're pretty sure that that pattern actually can be replicated. And then when I move from one size to the next, I can actually just do the same procedure that I did last time. And then I actually can show that I can solve any problem that you give me, because I can figure it out successively until I get to that number that I need. So what we had here is we saw that our base case was n equals 1. So the grid was 2 times 1 by 2 times 1 was a 2x2 grid, and it looks like this. And this is obviously covered because this is an L-shaped piece. You always want your base cases to be obvious. They might not be, but they usually are. And that's why induction is so useful, because we can solve a stupidly easy problem so that we can solve bigger, harder problems that we actually might not have thought that we could solve. Okay, so then we figured out how to do n equals 2. This is not required for induction, but it's normally what we have to do when we're doing a proof, because we need to figure out how we're going to map a small solution into a larger one. So it makes sense to go from 1 to 2, and then maybe 2 to 3, and 3 to 4. You have a question?
Yeah, I was wondering if you went 2 to the n, by 2 to the n.
Yes, I did.
2 and
Yeah, you're right. So, sorry, that's what I meant. It was 2 to the 1 by 2 to the 1. So the next one is 2 squared by 2 squared. Okay, so we figured out n equals 2, which was 4 by 4. And we drew it. But in the course of drawing it, you actually do draw the 2 by 2 case, right? Like before I finish drawing all the lines, I'm kind of drawing the 2 by 2 case. And in Robert's example, he said whichever piece the square is in, it's going to be in one of these, right? The empty square removed is going to be in one of those. So let's just assume whichever one it is. It's going to be this one maybe, but I just picked it arbitrarily. It doesn't matter. And pretend that that's an evenly spaced division. So here's a nice L-shaped piece. I like how you guys use an L, to show that that's an L-shaped piece. So that's a nice way to do it. When you come up with a good way of labeling what you want, let's stick with it and use it consistently. Okay? And then what he looked at and saw is, I can treat this like a missing piece back in the original problem, right? Because I figured out how to fill this with an L-shaped piece, and this looks like a bigger L-shaped piece. And if I can figure out how to tile this with L-shaped pieces, then I'm done. But this is basically an abstraction. I didn't actually have to have the fact that this is 4 by 4. This is just the next size up from whatever I did last. So if I can solve the previous problem, then I can solve the next problem, no matter what. So for n equals 2, we actually know that there's divisions here. And you can just look at it and figure out a nice mapping, which is, the first thing is to fill that one out, and then that kind of leaves these things left over. So let's write down what we actually did. So in an induction proof, we always have a part called basis, which we already wrote, and then we have an assume statement. So we assume we can tile a 2 to the n by 2 to the n grid with L-shaped pieces. And we want to prove we can tile a 2 to the n plus 1 by 2 to the n plus 1 grid with L-shaped pieces. Now, by the way, if you didn't get this, don't feel bad. The first time I saw this problem, I didn't get it either. I was taking a math class in Hungary, and I took a class called Conjecture and Proof. And we had problems like this every single night, and every day I would come back with at least one problem I couldn't figure out. And then they would show me some stupid trick, and I would be mad. So this is one of these fun classic problems. Okay, so what we kind of just did for the 4 by 4 case was we kind of reused the solution for the 2 by 2 case. So what we can do is, for this grid problem, we can say if we have the 2 to the n plus 1 by 2 to the n plus 1 grid, it is made out of a 2 to the n by 2 to the n grids. So each one of these is a 2 to the n by 2 to the n grid. So when I make a 2 to the n minus, so this height here is 2 to the n plus 1, and the width is 2 to the n plus 1. So that's actually how we make a 2 to the n plus 1 grid, is actually by putting 4 2 to the n grids together. So then you figure out which one has the missing square. And if it has a missing square, you already know that you can solve it because of the assumption. This is called the inductive hypothesis. Okay, an inductive hypothesis is exactly the same thing as the givens in a logic proof, like what we did earlier in class. So whenever I gave you a problem and I said assume you know A and you know A implies B and B implies C, then show that C is true. I have a question for you. Did you argue with the givens? No? Why not? I told you they were true. That's what we do with hypotheses. We don't argue with them. We assume that they are true and then show that if they were true, then the next thing's going to be true. So we don't have to know this is true yet to actually use it to show something else. Because all I'm actually trying to show is that the 2 to the n case implies the 2 to the n plus 1 case. And when we're trying to show an implication, we have two different ways to do it, remember? We have direct proof, which is where I assume my givens, and then I show what I was trying to prove is true based on those. Or I can do a proof by contradiction. We're doing an induction proof. We're not doing proof by contradiction. We're doing a direct proof. But it's basically by recursively using modus ponens over and over again. Okay, and I'll show you how that is in a second. But so we figure out whichever one the square is in. So whichever one the missing piece is in. And that is solved by the inductive hypothesis. Whichever one it is, it's solved by the inductive hypothesis. Everybody believe that? Why should we solve a problem again if we've already solved it? That's why you're in computer science, because we like computers to do stuff that we already figured out. And then we know that we have this giant L-shaped thing left over, which means that in the middle here, there's actually a 2 to the n by 2 to the n piece that's L-shaped, right? So by definition of, like, since this has already been taken out, there's a piece right here that can also be filled with the inductive hypothesis, right? So we know that by the inductive hypothesis. But then each of these also is 2 to the n by 2 to the n with a piece missing. Yes?
So is the inductive hypothesis given, or is that proof that you can...
It is given. So when I write down assume blah, 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 it's just like writing down a given in a logic proof. So it doesn't necessarily have to be true. It's just I'm going to assume it's true and then see if I can prove this. And then my basis is not given. I have to prove the basis. If I cannot prove the basis, then this part doesn't do anything for me. So let me go back to why that is true. But does everybody see how the inductive hypothesis actually gives me all these pieces no matter what the size of the grid is? That looks like a no, but we're not going to raise our hands. Okay, why don't you think about it some more? If you still have questions about it, ask me when I'm back in town. Also, there's a bunch of probably web pages with this proof on it because this is a really classic old problem, so you can look it up if you need some more different kinds of explanations. But let me go to why this is an application of modus ponens. Okay, so the way induction works is we have a basis and we have an assume statement. This is called the inductive hypothesis. And we have a prove statement. This is like what we're actually trying to prove. So in order to have an induction, we have to have all three pieces. So I'm going to be proving a statement like P of n, where n is a natural number, most likely starting at 0 or 1. And we have to have all three of these. So for the basis, what I'm going to prove is probably P of 1 or P of 0. So it's some predicate that depends on the value of n. So in our last problem, the predicate was I can cover a grid of size 2 to the n by 2 to the n with L-shaped pieces. That was my predicate that I was trying to prove, and n is a variable in there. So P of 1 was that I could cover a 2 by 2 grid with L-shaped pieces. And then I had to actually prove that that was true. I had to show that. It was easy because that actually itself was an L-shaped piece, but if it wasn't easy, I would still have to do it. Okay, then what we did is we assumed that P of n was true, and we proved that P of n plus 1 was true. So in our example, P of 1 was that a 2 to the 1 by 2 to the 1 grid is coverable by L-shaped pieces. So what is P of n? It's exactly the same thing, except wherever I have the n, this was usually given in your problem statement. So P of n plus 1 is to take that, whatever the statement for P of n is, and wherever there's an n, replace it with n plus 1. So remember that we sometimes do problems with robot brain and sometimes we use regular brain, right? This is a part for robot brain. So don't start trying to figure out what P of n plus 1 is. Just wherever you see an n, put an n plus 1. Because as soon as we start trying to mess with it in our heads, we can mess up where the numbers go. And I recommend putting parentheses around whatever had the n before so we don't mess up and put a plus 1 like on the wrong level or something. Now, when we actually proved the 2 to the n plus 1 case, or the P of n plus 1 case, we assumed that P of n was true. So what we actually did was we showed that P of n logically implied P of n plus 1. So we didn't actually prove P of n. We just showed that if P of n is true, then P of n plus 1 has to be true. Correct? That's what we did. Because we showed that if we could have solved it, then here's how we break it down. Here's how we break the n plus 1 problem down into an n-size problem, and we're assuming that that one can be done. So what we actually proved was if this can be done, then that can be done. And I've given you the procedure. In the proof, you have to give the procedure that lets you solve the n plus 1 problem using the n problem. If I don't have the basis, does this actually prove P of n? If I do have the basis, does it actually prove P of n for any given n? Okay, I want to take a vote. If I have a basis, does it prove it for any arbitrary n? Raise your hand if you think yes. One person thinks yes. If you have the basis and you have P of n implies P of n plus 1, does it prove it for any arbitrary n? Raise your hand if you think yes. Yes, any n greater than or equal to the basis case. Okay, all of you should be raising your hand because it does work. Why does that work? Let's see why. If I know that P of 1 is true, so when I construct an inductive proof, these are the two things I prove. I prove P of 1, if I have to do it with the truth table, if I have to do it with any other kind of arithmetic argument, whatever, I prove it however I can. I can draw a picture of how to do it. Anything that shows that I can do it works. And then I prove, just like we did our logic proofs where we write down givens and then we try to derive what we were trying to prove. We assume that P of n is true, and we show that P of n plus 1 must be true because of that. That's a proof that this implication holds. So therefore, let's say that n is 2. How do I get P of 2 out of this? Right, well, since P of n generally works for all n's, then I know that P of 1 implies P of 2, right? And I already know P of 1 because of the basis. So since I know both of those, what rule tells me that P of 2 is true? Modus ponens tells us that P of true is true. Well, once I have P of 2 is true, then I can show that P of 3 is true, right? And then once I have P of 3, I can show P of 4, and so on and forever. So as long as I have enough time, I could eventually get to any number that you want. This is how induction works. So it works on the well-structured nature of numbers. So if I'm going to go from n to n plus 1, it's always the same, right? I add 1 to the original number. So, and the same thing, in order for me to be able to prove P of n implies P of n plus 1, there's got to be some way that I can go from size n to size n plus 1 in a regular way. It's always the same when I go from one thing to the next. But numbers are like that, right? So that's how induction works, is it's built on the basis of this is how we go from one number to the next. We do it the same every single time. And since we do, we can use remote exponents repeatedly as many times as we need to. Yes? That's a general thing for all induction problems. So whatever the basis is will be P of 1 or whatever the basis number is. You can actually do induction proofs, so you could say, well, prove this for n greater or equal to 4, and then this first thing would be 4. So you can start your basis wherever you want, and you just write your statement that it is going to be true whenever n is greater than or equal to whatever that number is. But this is the structure of all induction proofs. So if you actually write an induction that looks like this, and you're able to show the basis n P of n plus 1, then you're actually done, and you don't have any more work to do. Okay, it's a really, really powerful technique. All right, so let's do some examples. So this is really abstract. I'm trying to make it concrete for you. One reason why we need induction is we have a lot of times things that we call open forms that actually we don't want to calculate because they're a pain. And we often try to write formulas for them and then use the formula instead of the open form. So let me give you an example. So there's an example of a problem I might want to sometimes solve. The sum of all the numbers from 1 up to n. Okay, so that's the sum of all the numbers from 1 to n. Would you like, every time I need that, to use this formula? No. I'd much rather have something where I could just do some multiplication instead. That would be faster, right? Like, let's imagine you have to sit there with your calculator. Would you like to punch this in or some formula? Formula, much better. So we don't like to do summations. We'd like to have closed forms for them. However, as computer scientists, we're responsible for showing that if we use a formula for something, it's equivalent to the original form. So that's what we use induction for, is that we say, we figured out a formula, we show it works for everything, and now we can use the formula instead. Which is similar to what we did with our axioms, right? When we proved by truth table that something worked, then we didn't have to use the truth table proofs anymore. We could actually just use that axiom. And that's very similar to what we're going to do with induction proofs for formulas. So does anybody know what the formula for this is? Let's figure it out. So we can actually figure out the formula. So if n is equal to 1, let's call this S of n. What is S of n? If n is equal to 1, what's the sum of all the numbers from 1 up to 1? 1. If n is equal to 2, what's the sum of all the numbers from 1 up to 2? For n equals 3, what's the sum of all the numbers from 1 up to 3? 4, 10, 5, 15, 6, 21. So we're already cheating, right? We're not actually recalculating every time we're looking at the previous value. Aren't we? Yes. So we're going to do some recursion later in the class, but we actually we're just using that S of n equals S of n minus 1 plus n. And S of 1 equals 1. So that's what we just did in order to construct this, right? Because when I was figuring out this number, I looked at that one and added n to it. Okay, that's called a recursion. A recursion is very similar to an induction because it's a formula that I can use that has a basis and it has a way of constructing new things out of old, smaller things. So induction and recursion are kind of interrelated, and we're going to do some recursion after we do some initial induction stuff. Okay, but let's see if we can actually figure out a formula that doesn't depend on a prior value. So one of the ways we do this with a formula is to look at consecutive values and see what the differences are. So we got a difference of 2 there, difference of 3, 4. That may or may not tell me anything, right? Because we already know what those differences are. We could also look for powers of 2. We can look for squares, those kind of patterns, to see if we can see something. So squares would be 1, 4, 9, 16, 25. That looks sort of close, doesn't it? Anybody have any ideas? So we could match up the first and the last one? Oh, okay. So you're talking about if we wanted to do, for example, we could pair that up. That adds up to 7, right? And this adds up to 7. And this adds up to 7. That looks good. So we have n plus 1, right? That's 7 times n over 2. And that should work for all the numbers. So that's a nice, clever matching up argument. And this is a really often used trick in CS2, is to look at the smallest thing and pair it with the top thing, because that's a property of numbers, is that the sum, of two numbers is always going to be the same if they're symmetric across the middle. So this works. So this is the formula for this. Now we need to prove it by induction if we want to use it forever and ever. Okay, so here's what we want to prove by induction. We want to prove S of n equals 1 plus 2 plus ... plus n equals n plus 1 times n all over 2. That's what we're going to prove. And we're going to prove it by induction on n. So n is the thing that's allowed to change from one thing to the next. And so we always do this formula where we write the basis. So we figure out what is S of 1. So I actually figure out what n value I want to start with, n equals 1, because a sum up to 0 doesn't make any sense. I could probably define it, but I'm just going to start at 1 because that makes more sense. So we know that that just equals 1 for my left-hand side. And for my right-hand side, that's going to be 1 plus 1 times 1 all over 2, which is 2 over 2, and these two things are equal. And I like to put a little check mark to show that I checked them and verified that they are actually equal. Super easy case, right? Then we write the word assume, and then we copy over the statement we're proving. This is robot brain work. And then the prove is writing this is also robot brain work. So wherever you see an n, put an n plus 1. Don't do any of it in your head. Just copy. Wherever you see an n, put an n plus 1. Okay, and then it's nice if we can rewrite this into something readable, right? So that's n plus 1 times n plus 2 over 2. So I like to use the abbreviation LHS for left-hand side and RHS for right-hand side. So the basis is a separate part of the proof. Now remember that just like our logic proofs, we're going to think of this assume like a given, and the proof is like the thing at the top of the page that I'm trying to get at the bottom of the page that will actually be true. And I'm allowed to use any regular math in this proof. And that's pretty much the only kind that we have to do. So there's a little procedure I'll give you that makes doing induction relatively straightforward for math formulas. And that's good because that's what almost all your homeworks are. Almost none of them are cool pictures with L-shaped pieces. In fact, exactly none of them are. You wouldn't want to do that on WebAssign, I'm sure. Okay, so this is our problem setup. Now, if this is a 10-point problem on a test, points are allocated for each of the parts. 2 points for writing down the basis and actually proving it, 2 points for writing down the assume, 2 points for writing down the prove. So use your robot brain and get your 6 points out of 10. Okay? That's right. You can get a D without doing any work. All right, now the next part we need to do isn't that hard, so I'm going to teach you how to do the other 4 points. Okay? The first thing I do is I start with the left-hand side of the proof. Or whichever one looks easier to write in terms of the other one. I think a sum looks easier than a product. So I'm going to start with the sum. And then what I'm going to do is I'm going to set it equal to the left-hand side of the assume statement. It's going to be wrong at first. Then we're going to fix it. So they're not actually equal yet. We're going to do whatever brain work we need to do to figure out how we fix them to be equal. This is relatively easy, right? I just have to add n plus 1 and they will be equal. Does everyone see that? So this is what I added on. So this is the left-hand side of the assume, 1 plus 2 plus dot, 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 plus n. And then I just added an n plus 1 term on there, because that is the difference between these two sums. Now what I'm going to do is replace the left-hand side of the assume with the right-hand side of the assume, because I actually assume that equality holds. So I'm going to replace that with the right-hand side of the assume. And I'm not going to do anything with this anymore. This makes me happy because it gets this part of what I need on the paper. So my goal is to get the entire proof statement written on the paper as two things that are equal to each other. So I've got the left-hand side. Now all I have to do is do work until the right-hand side looks right. Okay, so I'm going to replace the left-hand side of the assume with the right-hand side of the assume, which is n plus 1 times n over 2, and then just copy down the rest of it. And it's nice to keep in view what you're trying to prove, just like when we did the logic proofs. We always want to keep in mind what we're trying to prove and make the thing we're working on look more like that all the time. Okay, now I look at what I'm trying to prove and I see that there's a factor of n plus 1 in there, and I see that there's n plus 1s in both of my terms down here. So you have a couple of options at this point. You can multiply everything out, redistribute, and see if they're equal. I don't like to multiply things out because I make mistakes. So I like to factor things when possible, so I see that there's an n plus 1 in both terms. So I'm going to factor it out and see that we get n over 2 plus 1. So that's just like taking an n plus 1 out of here. I get n over 2 left. If I take an n plus 1 out of this term, I get 1 left, because that is actually n plus 1 times 1. which I can use anytime I want to. What do we do next? If I'm trying to get a statement to look exactly like the right-hand side of the proof, I need to have a 2 in the denominator, right? So I need to get a common factor inside these parentheses. Common denominator. What's the common denominator? It's a 2. So I have n over 2 plus 2 over 2, right? So I copy over the n plus 1, and then I get n over 2 plus 2 over 2, which is equal to n plus 1 times n plus 2 all over 2. Is that what I was trying to prove? Yes, it is. There it is right there. They are the same, except what? I reverse the order, but I'm allowed to do that? It's close enough for government work, which you don't get paid for or get to do this week. Okay, so it's close enough. If you really want to, you can, write another equals and put n plus 2 times n plus 1 over 2. All right, so now we've done our first induction proof. Almost all the ones you'll get are going to be just like this. So you can, even if you read a problem and you don't know what the heck it's even saying, you should be able to do an induction proof anyway. At least the setup. And starting with the left-hand side of the proof, setting equal to the left-hand side of the assume, and doing a fix, and doing a substitution. You can do that much of an induction proof without knowing what the heck it's talking about. Yes?
When you on the test scenario are you going to ask something along the lines of prove that when you sum numbers between 1 and n that it's going to work, or are you going to say prove that for a given n plus 1 times n over 2?
I will usually give you, on a test, I'll give you a formula. Like I'll actually give you the statement, the induction statement, and you have to prove it by induction. If I have you derive a formula, that'll be a separate question. So you will never have to derive a formula and then prove it right there, because I always think that if you derive a formula but it's wrong, then you're going to spend all this time trying to do the induction that won't work. Because induction won't work if it's not actually true. Okay, induction will only work if it's actually true. You might actually think you've got an induction proof, but it's actually, there'll be something wrong with it. So, any questions on this one? We'll do another one. All right, so we'll go to another one and see if we get some questions on that. So here's another formula we want to prove by induction. So let's use robot brain and write our basis down. So you might not know exactly what to write down for n equals 1. So what you should do is go to your formula and plug in a 1 for that last term. And we get 0 times n, times 1. On the left-hand side, are there any terms before that? No, there aren't. There aren't any terms before that because this starts at n minus 1 equals 1. So there's no terms before that. And I can put over here a 1 minus 1 over a 1. And this is equal to 0. This was the right-hand side. That's equal to 0 over 1. And this works. So if you have a funny feeling and you think that's cheating because there weren't any 0 times 1s in the original formula, you may also start at n equals 2. You can start at any n you want to. So I wrote prove it for n greater than or equal to 1, but it's fine if you prove it for something else. So if you want your stuff to look more like the formula, we can try n equals 2. So we plug it into here, and we get 1 times 2. And that makes sense, and there's no more terms than that. And that's my left-hand side. And on my right-hand side, I should have 2 minus 1 over 2. There might be an error in my formula here. It might be times 2. Let's figure out a table. So I'm going to put 1. So on the left-hand side here we should just get 2. And for 3, we get 1 times 2 plus 2 times 3, which is equal to 2 plus 6 is 8. Okay, and let's look at n minus 1 over n. So 1 minus 1 over 1 is 0. 2 minus 1 over 2 is a half. And 3 minus 1 over 3 is 2/3. This is not looking promising. I printed this out. There's something wrong on this. All right, let's see if I can figure this one out real quick. If anybody can figure it out, it might be. Like I said, there's a typo on my stuff. Okay. Okay, well, since I have a mistake here, I'll just do a different problem. Who's ever seen that before? Everybody, right? If you're not raising your hand, you're lying because you took calculus before you took this class. And you're required to do summations in there for integrals, right? So don't pretend you don't know what these are. You might like to, but I know you're lying. Okay? So the problem that we did initially was this problem, not that problem. It was this problem. Okay, so that's the problem that we did. One of the things you're going to have to do for induction is actually figure out when a sum, what the induction looks like, what the summation looks like. Because if we don't do that right, we might not actually solve our problem correctly. So what I do to figure out what an induction is, what a summation is I need to think of a summation like a for each loop. Okay? It's like a for loop where this letter here is my loop variable. It's my loop counter. And I'm going to maintain a sum that starts out, it's initialized to 0. So the code for this is sum equals 0. For k equals 1 to n, I'm writing pseudocode, sum equals, let's do that. All right, so that's pretty much what my summation is going to do. So it's going to keep a running total and keep adding on whatever formula is in here over and over again. Since it was a k inside there, that's what we do. If I change that and I put some other function in there, like k squared, then I still just do that. So the summation means keep a running total where you're summing consecutive things, and the things I'm summing are formulas that depend on k. Okay, so whenever you have a summation, that's how you can translate it into a for loop, if that works better for you. So how about okay, so how about this? What does this give me? Summation k equals 1 to 4 of 4. It does not give me 4. It gives me 4 terms, and all the terms are 4. So the counter on the summation tells me how many terms I have, and the formula inside tells me what each of the terms is. If it doesn't depend on k, then it doesn't change. So that's why you have to be careful when you write summations. If I write this, that term in the middle doesn't change. So if I write summation k equals 1 to n up of n, that is actually just k times n. Because there are k terms and all the terms are each n, so it's going to give me kn. So in order to figure out how to write a summation out of a formula like this last one we had, you need to figure out, what do you think is going to be in the formula for if I write this as a summation? What am I going to put in here? K minus 1 times k? I usually look at the last term of the sum and put a k in there. By the way, I like to use k instead of I because when you write i's, they look like ones, and then it's confusing. So I use k, which never looks like anything else, hopefully, depending on your handwriting. Okay, so it's going to be a summation from k starts somewhere and goes up to somewhere. Where does k start? Well, I might just start it at 1, but if I plug in 1, what do I get? I get 0 times 1. It doesn't actually start there, right? It starts at 2 and goes up to n, right? Now, we're not done when we do that. We have made a guess that this summation actually equals that. So I should actually write out what I get. Okay, so if I set n equal to 2, then I'm going to get, I start with k equals 2, the term is going to be 1 times 2. That looks good. So, and I'm done. So that's the only term in the sum if n equals 2. So if n equals 3, then for k equals 2, I have the same thing, 1 times 2. For k equals 3, I have 2 times 3. Looking pretty good, right? So you should check. When you make your summations, you should check and make sure that they line up with what you were trying to use them for. The reason for that is occasionally there are more terms than you realize. Those dot, dot, dots can hide stuff. And you need to make sure that the number of terms is actually matching up with what you actually write your summation for. One last thing before you go, I did want to let you know the summation notation is used for other stuff too. If you have a giant pi of some formula, that is the product, the running product. if you have this big intersection, and this is a set, then that's going to be the running intersection. So that'll be A1 intersect A2, intersect ... intersect AN. And if you have the union, you get the same thing, same kind of thing, except the operator is a union operator. And you have some problems like this. So one of your problems for homework 5 is to prove De Morgan's for an arbitrary number of sets with induction and this notation. We actually already proved it for 3 in class before, and you can use that to prove the inductive case. See you next time.